Hi there, this is your favorite math learning channel, and I'm back after kinda long time with my shitty laptop camera. This is just a test video. I'm just trying the camera, whether if it works. I don't know if it's gonna make the presentation better. We're gonna see. So we are supposed to find if this limit exists. Well, here the first part is just adding reciprocals of integers. This is hn, which is called harmonic series, which diverges to infinity. And this is just an increasing function, which also goes to infinity, of course. And well, it's actually surprising that this limit actually exists, and it's shown with a Greek letter gamma, which is called Euler-Mascheroni constant. I don't know if it's Mascheroni, but I know Euler well. He's my favorite, which is about 0.577, and it just goes like this. And well, it's also not known that whether if this is rational or irrational. It is left as an exercise to the viewer. Yeah, maybe you can find it. So here, well, we have difference of two stuff. Maybe if this thing is monotonic, which means that whether it's increasing or decreasing, then if it's increasing, we can try to find an upper bound because it's like increasing and there's a peak. Now I'm tempted to show it with my hands, but let's show it here. So for example, if a function is increasing and it is limited above, it's convergent. If a function is decreasing and it's limited below, it's also it has a limit. I don't know what I said before. This thing is convergent. Okay. So let's see if we have such case. What is that? Okay. So let's delete this thing and start. So let's just call this whole thing an. Okay. An. And we are gonna see if this limit exists. So first we are gonna check if this is increasing or decreasing. Well, it's of course not wise to look at an plus 1 over an because it's just, I mean, it's complicated stuff. If we had like some terms multiplied, we would look at an plus 1 over an. But here it's just much better to look at an plus 1 minus an. So here I have just hn plus 1 minus hn. Well, let's write this directly. So if I put n plus 1, I'm going to add n plus 1 terms. And if I put an, it's adding n terms. And if I just subtract them, I will get the n plus 1 term. You can just try to imagine this part. So it's going to just give me the n plus 1 term, which is 1 over n plus 1. So this is from the first part. And from this part, so I'm putting minus first an plus 1, which is minus ln n plus 2. And well, and from this part I'm gonna get minus plus, so it's gonna be just, let's directly combine them. So this is gonna be ln n plus 1, which is directly this thing, and the other one is minus ln 2 minus ln n plus 2, so I can just take it here. Okay, and now my goal is to show whether if this is less or greater than 0. Okay, there can be equal signs too, I don't know which one. And actually here I'm not allowed to use calculator. I don't like calculators, at least while doing the math. Well, I use it a lot. Here, for example, you can just write some values. Just put n is equal to 1 and then put n is equal to 2 and see if it's bigger or smaller. And then you can make a better guess. Here, if you can try, well, I didn't try putting such values. This is decreasing, okay? Let's try to show this is less than 0. So, well, wait, this is actually increasing, sorry. So, well, the like most basic inequality about natural logarithm, which is actually the way it can be defined. We can just define it with its multiplicative property, ln ab is equal to ln a plus ln b. And the second second part is just inequality, which says ln x is less or equal than x minus 1. Whenever x is just defined, I mean here ln x is defined when x is greater than 0. Okay, so this is true for any positive x. And so here, well, I don't know about this part because I want to show that this thing is greater than 0. Well, I can just use the property of ln. So instead of x, if I put 1 over x, this is true. it's less or equal than 1 over x minus 1. Why am I doing this? Because now I got an minus sign. Do you notice it? So I can just write 1 over x as x to the minus 1, and I can take it here. So now if I just multiply both sides by minus, I'm going to get ln x is greater or equal than 1 minus 1 over x. Cool. So I'm going to keep this thing. And now, so also let's write this part. My x part is just n plus 1 over 2. I can just add 1 and subtract 1 here. And so this inside is just going to be ln of 1 minus, so I just added 1, subtracted 1, 1 minus 1 over n plus 2. So this thing would be just greater or equal than, it's better to just write it normal. So this is just n plus 1 over n plus 2. So this is greater or equal than 1 minus this thing flipped. If I flip this, it's n plus 2 over 1. And now I can just separate that 1, and it is going to be just 1 and plus 1 over n plus 1, which is equal to, just these ones would cancel, and I would get 1 over minus 1 over n plus 1. So I found that 1 over ln this thing is greater or equal than minus 1 over n plus 1. So this is greater or equal than, so this thing is just same, 1 over n plus 1 minus, so this is just minus of that, which is equal to 0. So I found that an plus 1 minus an is greater or equal than 0. Cool. So this means that the function is just increasing, okay? It just gets bigger and bigger. So like I said in the beginning, if a sequence is increasing and it's also bounded above, it's going to be convergent. So now our goal is to find an upper bound. Also a note here, if our function was given as ln n, you can just try to work this out, okay? Instead of ln n plus 1, if I was given ln n, this sequence would be decreasing, and it would be very easy to just find lower bound because it's just positive, okay? So I could just say 0 is less or equal than hm minus ln n, and you would be done. But why would we do easy thing when we can do it harder, okay? So I'm sorry about that. So I found that our sequence is just increasing. Cool. So this is the first fact. And the second fact, we are going to use a theorem that I also used before. It's mean value theorem for integrals. So this basically says that integral from a to b of, let's say, a function fx dx. So there exists a c. Well, normally I should have just put this part before. There exists a c on the interval of a and b, such that this thing satisfies, okay? This integral is equal to b minus a times fc. So there exists a perfect c value in the middle. Let's try to make sense of this. So for example, I have a function like this. It doesn't have to be increasing. I mean, anything would work. Any continuous function would work. So I have that, for example, the integral from a to b is just this area, right? Which is, let's show it like this. It's very unprofessional, but it's just to see. There exists a perfect height, c, such that, for example, it's here, that if you take this height with the same width, these two areas are same, okay? It makes sense. So this is what it's telling us. And we are going to use this fact. And here, how are we going to choose x? Well, it's actually not so easy to guess it. Well, basically, we can just guess two things. Let's guess the function 1 over x, and let's guess the function ln x. Here, the second one works. So we are going to choose the function of ln x dx. Why? Because it works, okay? And well, for the bounds, like generally we would pick like maybe a and a plus 1, so that the differences would just be 1 and we would be able to add integrals. But here we just want to kind of want this thing to vanish in the end. So we actually want to pick something small. So what we can pick is that 1 over n plus 1 and 1 over n. So we are picking something small, okay? And so by this theorem, we can say that there exists a C between these bounds, which is between 1 over n plus 1 and 1 over n, such that this integral is equal to b minus a, which is again 1 over n minus 1 over n plus 1, the function at c, so ln c. Also here, well, we like, instead of just using c because the n could change, let's choose this c depending on n. This is just a detail, okay? We didn't have to do this. And now, so we found an equality for this integral. And also this integral is very easy. I'm not even gonna do it. You can just do it by integration by parts. This integral actually equals to x ln x minus x. So this integral 1 over n plus 1, 1 over n ln x dx is also equal to, so we are just looking at this thing in two ways, okay? A and b. And then in the end, we are just going to say all these two are equal. So this integral is equal to x ln x minus x. And we are just going from 1 over n, 1 over n plus 1. Cool. So now I'm just going to substitute them, and we're going to see how good it gets. So if I put 1 over n, 1 over n, ln 1 over n. Here I'm going to be lazy and just skip some steps here. So I have ln 1 over n here, and 1 over n means n to the minus 1. So I can just flip it and get a minus here, okay? So it's my 1 over n. What is this? So this is 1 over n ln n. And let's also do this here, okay? So I have that 1 over n plus 1, 1 over n plus 1. So from the natural way of the, like, this bounds, this thing is just going to get minus 1 over n plus 1. And ln of 1 over n plus 1. So I can also flip this thing, and I'm going to get another minus. So this thing is just going to be plus n plus 1. Okay. And, well, there other two terms are just easy, so I'm going to get minus 1 over n, and other one is just going to be minus, so it's just going to be plus 1 over n plus 1. Okay, cool. So here I want to group these stuff such that in the end I just want to actually say this thing, this whole thing, is equal to the previous result that I found. So I actually want to factor this thing, like 1 over n minus 1 over n plus 1 from this thing, okay? So here, well, I can do this part easily. It's just that thing times minus 1. And for this thing, so, well, I will also do this on this step. Here, what I need is that, well, this thing has a constant of 1 over n, the coefficients of 1 over n, and this thing has 1 over n plus 1. So I can just multiply this thing by n plus 1. Okay, how do I do that? I just also multiply it by n plus 1, and I'm just going to take the power here. Okay, so this is ln of n to the n plus 1. I'm not going to put parentheses. And for this part is same. I'm going to divide it by n and multiply by n, and I can just take this n to the power. So now they're both on the 1 over n times n plus 1 parentheses, and this thing is actually also equal to 1 over n plus 1. If you imagine these two are just same, okay? This thing would be equal to 1 over n minus 1 over n plus 1, so it's just minus of that. Well, if you do integration by fraction decomposition, you would know this. So here, what did I say is that now I'm just going to factor it. So I'm just going to take 1 over, so this thing is just equal to minus of this thing is just equal to this thing alone. So let's just write it like this, okay? 1 over n plus 1 at this parenthesis. So I have first this term. Let's write this one. I want to go with the positive first. So I have ln of n plus 1 to the n. And now minus this thing. So if it's minus that thing, minus ln something, I can also just take this here, okay? N to the n plus 1. And so like I said, this thing is just -1. The rest of the terms are just -1. Okay, cool. And again, so I said that this thing is also equal to 1 over n times n plus 1. So this is just 1 over. So now I'm just using the previous result. This is equal to 1 over n plus 1 times ln cn. And these are just same and they're not 0. I can cancel them. So now what do I get is that ln of cn is equal to this thing. And well, I can just take both sides on power of e, so that I will get something more simplified, because this is power of ln, this is using ln, this is using ln. So it will just be simpler. So if I take ln of, if I write all sides by power e, so this thing is just going to be cn equals to, so e to do this thing is just, I mean, e to the ln something is just that thing itself. So this is n plus 1 to the n over n to the n plus 1. And I can also just write this thing as, I will just combine this again. So it's just, this thing is just n plus 1 over n to the n. And I have just 1 over n extra. So I just wrote this thing. And this is just, so I'm just writing this thing again to the power of e. So this is just e to the -1. It's just multiplied, imagine. So this is just 1 over e. And I can just put the e here, okay? So this is true for so for any n, well, I didn't choose an n, there exists a cn sequence such that this is true. And also if I rewrite this, this is just 1 plus 1 over n to the power of n times 1 over en. Also, this looks similar to how the limit definition of e. Well, we know that limit as n goes to infinity, 1 plus 1 over n to the power of n converges to e. So we're actually going to get something like that. We will get a bit more advanced version of it. Yeah, and then you can brag your friends about that. So here, well, I want to simplify this for e, so I'm just going to multiply both sides by e and divide by cn. So I'm going to get that e is equal to, so I just swapped e and cn, okay? 1 plus 1 over n to the power of n, 1 over cn. Wait, cn times n. Okay, cool. So now, well, again, like I said, if you take limits, well, probably this thing will just go to 1 and this thing just goes to e. So this is true. Okay, so this is like a bit more generalized version of that limit. And well, I will not do that this limit goes to 1, because you can just use this thing. Okay, so you can just flip all sides. It's just going to be n plus 1 and n, and divided by n. So they're just going to go to 1. Okay, so this limit is of course 1. So I'm actually just taking ln on this step. Okay, let's do it here. So I have ln e, right, which is equal to 1, and I'm taking ln here. So this is just gonna take the power to the before, like as constant. So this will be n ln 1 plus 1 over n. And this thing is just going to be plus because those things are multiplied. So it is just going to be ln of 1 over n cn. Okay, cool. So I have 1 is equal to this thing. And so again, what is my goal actually? I want to show that I have sums of 1 over k's, right? So I can just convert this thing into 1 over k's. So let's try to do this. Well, on this step, instead of n's, I'm just going to put k, okay? Let's just put k's. And so instead of any n, not for this ln n, I'm just going to put k. Wait, what was here? So this was k, this is k, and this is k, and this is k. Nothing has changed. because I just don't want to use the same in this again. And now I'm just going to divide all sides by k and then add it up to k. So I'm not using this part, okay? It was just to simplify, to clarify it. So I'm just dividing all sides by k. What I'm going to get is that 1 over k is equal to, so this thing is just going to cancel. It's going to be, let's write this, okay, let's write it same, 1 over 1 plus 1 over k. And this thing is just 1 over k ln 1 over k ck. Okay, so now again, I just want to add all sides. K is from 0, wait, I can take from 0, from 1 to n. K is from 1 to n, so that I'm just getting hn. Well, I'm kind of close. So I want to show that this limit exists. And here, what I can do is that, so I will just rewrite this thing, okay? So this is just k plus 1 over k, right? K plus 1 over k. And if I actually write this thing, k is from 1 to n, this is actually telescoping because it just gives you ln of k plus 1 minus ln of k values. And I have this thing, okay? 1 over k ln 1 over k ck. And well, if you add this thing, so imagine like if you put 1, it's just gonna give you ln 2 minus ln 1. If you put 2, they are just gonna cancel, and I'm gonna get the biggest term of the first one and smallest term of the second one. So this is just gonna be ln of, so if I put n, it's gonna be n ln of n plus 1. And from this part, I'm just gonna get minus ln 1. So the first case was ln 1, so it's just 0. I'm not gonna write that. So I have plus 1 over k ln 1 over, also I have sigma. Well, not for this part, but for this part. K is from 1 to n, 1 over k ln 1 over c k k. Okay. So now I'm kind of done. I wanted to get this thing, so I'm just now subtracting ln n plus 1 from all sides. K is from 1 to n, 1 over k minus ln of n plus 1. This ln of n plus 1 is independent from the sum, okay? You can think it like this. And now, so this thing is just equal to this thing. What's left here? K is from 1 to n, 1 over k ln 1 over k ck. Cool. So like I said, we found that this thing, it was increasing, and we wanted to find upper bound, so we just expressed it in different way. And now we want to show that this thing is less than something, okay? And if we can show that, we are done. So how can we do that? Well, let's zoom out a bit and see it in the bigger picture. So well, I don't have any inequality for 1 over k, but for ln, so like I said before, we have that ln x is less or equal than x minus 1. So ln of 1 over k ck is just going to be less or equal than this thing minus 1, right? 1 over k ck minus 1. And well, if you remember, ck was between, well, I remember 1 over n plus 1 and 1 over n. So I want to get 1 over k ck. Also, let's make this one's k. I mean, I just made all of the n's into k plus 1. So I want to get 1 over k ck. So I'm just flipping all sides. So in the end, I again ended up doing this thing. Remember, I didn't want to show this limit was equal to 1, but I'm still doing the same thing. So if I just flip all sides, well, so you would get 1 over ck. Your inequality would just change signs, but I'm just going to change the terms. So I'm just flipping this thing, k, and flipping this thing, k plus 1. And now I'm just dividing all sides by k, all sides by k, all sides by k, and I'm just gonna add 1 to all sides. So this is my goal. So this is gonna be that if I just add -1 to all sides, -1 to all sides, so it's just gonna be 0 less than 1 over k ck minus 1, which is less than, so this thing is just equal to 1 plus 1 over k. So I just did -1, so this is just gonna be, so I just did -1 on all sides, also on these sides. It's horrible writing, sorry. So these ones canceled out and I got 1 over k. So I found that this thing is actually less than 1 over k. Cool. So I found that ln of this thing is just less than 1 over k. So I can say that this thing is just k is from 1 to n. I hope that you don't hear the sound from outside. It's horrible. 1 over k. And this thing is just less than 1 over k, so it's just k squared. And well, I also want to make a video about this thing too. So this is very famous sum, the integers from integers 1 over n squared. The king earlier solved this problem, which is called Basel problem, pi squared over 6. So if you add infinitely many terms, this will converge to pi squared over 6. So you can just say this thing, well, if I add finitely many terms, it's of course less than pi squared over 6. Also, this is also just for showing off. You can say, for example, this thing is equal to, I guess, 1.6, I'm not sure. So you can just say it's less than 5. Of course you can do that. You can just say, instead of doing this, you can say it's less than 5. But it's ugly. This is beautiful, okay? So, well, now we are actually done. I showed that our sum, which was hn minus ln n plus 1, is less than pi squared over 6, which is zeta 2. I will also make a video about that. So we found upper bound, and we also show that this thing is increasing. So again, if I draw a shape, it's increasing and bounded above. So this thing is convergent. And how do we know that it's convergent to this thing? Well, this is the tricky part. You can't actually know that. So basically, to find that, you would kind of need like a different representation of gamma. For example, you would need, I'm just like saying it randomly. For example, you would have an integral. I don't know such integrals, but surely there are many. If you just Google this constant, Euler Masonry constant, you're gonna get that. Or just write Euler constant. But yeah, Euler was too big to just have him with one name. So for example, you're just gonna have a function fx dx, and for example, you're gonna given that this is equal to the Euler this constant again, and then for example, you're gonna do some steps on this integral, and you're gonna find that this is equal to limit of this thing, okay, limit as n goes to infinity, hm minus ln n plus 1. If you get this thing, then you're gonna say this was given. This is how it's defined, so this is equal to gamma. This is kind of the only way, or you can just calculate it numerically. Okay, and also lastly, so I said that, let's make a quick note, side note. I said that hn minus ln n plus 1, which is what we calculated, this is actually convergent. These two actually, this would just converge to gamma, but this thing actually also converges to gamma. So let's just show this difference. So, well, so for example, I know that hn minus ln n plus 1 is convergent. Okay, I just showed that this is convergent to, let's say, this constant, okay, n plus 1. So I can just say also this is true for any a, okay? Okay, I will just show the logic. So I can just say that then, well, I want to show that this is convergent to hn minus ln n. So I'm going to put minus ln n and plus ln n. So it's just the same thing. This is equal to hn. So I want to keep this minus ln n part, because this is what I want. and I'm just going to combine the rest. So this is just going to be plus ln n over n plus 1. And well, if I just take limits as n goes to infinity, I know that this limit exists, 1, and well, this whole limit is exists because this is just equal to the top thing, okay? I know that this would just converge to gamma again. This is actually y letter, okay? Just fancy Greek way. So this thing would just go to, sorry, it's the inside is 1, so ln 1 is just 0. So it wouldn't change. Also, yeah, you can just do this for any n plus a value, okay? But I think a should be positive, because if it's negative, you may, yeah, you're gonna get some terms that is undefined, okay? You can just put n is equal to 1 and a is minus 3. It's not gonna be defined, and there will be a problem. Yeah, I guess it's a good place to stop the video. So it is convergent.